Okay, so we know how to solve a linear system with the LU decomposition or Gaussian elimination. We know that the solution exists and is unique if and only if the matrix of the left-hand side is non-singular. But for the LU factorization to work, you need all leading minors to be non-zero, which is a much stringent condition. But then, if one of the leading minors is not exactly zero, but is small, is close to zero, it's also not very good for stability. Because if you divide by a small number, you get a large number, and this can lead to the loss of accuracy. So in fact, having leading minors close to zero is really, really bad for stability. Okay, so there is a way of alleviating these problems, and the main idea is fairly simple. You have your matrix, and you're using leading elements to eliminate the unknowns. So let's see. So at each step we find the element which is large and use it to eliminate other coefficients. There are several possibilities. In this strategy, which is called partial pivoting, you look for the element with the maximum absolute value along the column you are transforming. For example, if you work with the first column, then what you do, you scan the first column to find the maximum element, let it be A31, and then what you do, you swap the first and the last rows, and then you proceed as usual. Now, what's the complexity of this? You need of the order of m comparisons, exactly m-1 comparisons, and this is cheap. This is much less than the quadratic number of multiplications you need to do to eliminate, to zero out the contents of the column. So this is cheap. One other possibility is the so-called full pivoting. Here you look for the element with the maximum absolute value across the whole matrix. So for example, if it's this A3M, what you do, not only you swap the first and third equation, you also relabel the unknowns, which amounts to swapping the first and the last columns of the matrix. This is not very cheap, because for each column you need to do of the order of m square comparisons. And this is comparable to the complexity of eliminating the elements from the column. Because of this complexity, full pivoting is very rarely used. Normally you would use full pivoting only if partial pivoting fails, and most likely if partial pivoting fails, you have a much bigger problem which full pivoting will not solve anyway. You need to change the algorithm. Okay, so let's go back to column pivoting and let's see how we can fit it into the matrix formulation of the algorithm. For this I will need permutation matrices. So what's a permutation matrix, or more precisely an elementary permutation matrix, is obtained from an identity by permuting two rows. So for example, when m equals 3, we can construct p12 by exchanging these two rows, or p13 or p23. And we can do it for any m. Right. So how do they work and what are they useful for? Let's see, if we take this pKl and act with it on the matrix A, what it does, it swaps rows number k and l. If we right multiply a matrix by the permutation matrix KL, it will swap columns. then we can cast the Gaussian elimination with pivoting as a sequence of multiplication by these triangular matrices and permutation matrices. So the process of constructing the LU factorization looks like this. We start with our original system of equations. We find the pivot for the first column, which is equivalent to multiplying by this P1. Then we left multiply by the triangular matrix to annihilate the column, and we proceed. Then at the second step, again, we find the second pivot and then annihilate the column. So if we look at the step number K, suppose we are working with the column K. It means that this part of the matrix is already done. This is the column we're working on, and these are all zeros already. So we find the pivot, say will be IK. We take this element, we bring it to the top, and then eliminate the column. And when we do it m-1 times, what we have is the result. Our upper triangular matrix U is given by the product of original A and a string of these permutation matrices and triangular matrices. It is intuitively clear, and it's not very hard, even if tedious, to prove rigorously that what this actually generates is an LU decomposition of a matrix which differs from A by some row permutation. So this is A, which is right multiplied by some permutation matrix. Or more traditionally, it's written in a slightly different form. It's written like this. You have your matrix A, and you decompose it into the product of a permutation matrix times something which is lower triangular times something which is upper triangular. And you can actually prove that as long as the matrix A is non-singular, this factorization exists. So in other words, if your matrix A is not singular, then there exists a permutation which makes all leading minors to be non-zero, and then LU decomposition works.